Okay, so the plan for today is to continue on with Chapter 8, Rational Expressions. We'll discuss multiplying and dividing rational expressions and adding and subtracting rational expressions with like denominators. And next week, we will finish up Chapter 8, adding and subtracting with unlike denominators, and then simplifying complex rational expressions. So Chapter 8 will also be a good review of factoring. So we have the Unit 2 exam this week. If you haven't completed it already, I recommend, you know, planning a time in the next few days to complete the exam. I recommend not waiting until Monday or Tuesday, as that doesn't really give you much time at all in case anything were to go wrong to get that worked out or fixed. So that exam, Unit 2 exam, is due on Tuesday the 30th at 11:59 p.m. But ideally, you want to complete that well before that due date and time. And then the week of Friday the 3rd through Friday the 10th is final exam week. I extended the window a few days earlier than the technical start of final exam week, just so that you have that weekend in case the weekend works better for you. Final exam, same setup as exams 1 and 2. Take it on WebAssign using Examity. The sample final is currently available, so you can check that out for, to help you prepare or study for the final. And same caveat as I just mentioned, don't wait until the last day or so to complete the exam, or even really the last couple of days. I'd recommend taking the exam at the latest, planning to take the exam at the latest Wednesday the 8th. And then that way, if anything pops up, you have some buffer, so that if, say, a technological problem pops up, you can find an alternative. You can get the tech worked out. If something personal comes up, you have a couple of days of margin to get that worked out before the due date. So there are no due dates extensions on the exams, and that especially applies to the final exam, because I need to have final exams graded, final course grades compiled, and uploaded in a pretty quick turnaround. Okay, so the quote of the day today is maybe a little less applicable to this class. It's more about something that we're talking about in stats, but I think generally in all of math, we have to be very cognizant of our assumptions. So we have certain frameworks or certain theorems where we say, okay, if I'm in this situation, I apply these ideas to get, say, a solution or to move forward. And we just recently saw with quadratic equations, if we try to use kind of the linear equation strategy where we isolate the variable terms, we kind of get stuck if we're in quadratic equations. So we have to realize that kind of the linear equation strategy works for linear equations. We have to be in that scenario where we're dealing with a linear equation for that strategy to work. That's kind of an assumption for those set of steps to solve the equation. If we are dealing with a quadratic equation that is not a linear equation, we don't want to go through and just isolate the variable terms, isolate the variable, and simplify. That's not going to work so well for a quadratic equation. So we need to be very aware of the assumptions that we're making. And this idea of correlations just is an idea in stats of how different things might move together. So for instance, different stocks in the market, some of them tend to move together. Some of them tend to, when one of them is high, the other one's high, and others tend to move in opposite directions, that when one is high, the other one tends to be low. And if we buy a whole bunch of stocks, if we buy, say, a collection of 100 stocks, we probably have, on any given day, there might be 1 or 2 that are doing well and 1 or 2 that are doing poorly, and they kind of cancel out. So we are exposed to less overall volatility, but so that's what we would call a negative correlation between those, so that there's some offsetting. But one of the assumptions in this kind of statistical model that says we shouldn't put all of our eggs in one basket, if you've heard of that adage before, or that you should diversify, if you've heard people say that, diversifying your portfolio. one of the caveats is that the assumptions of those models are that the relationships between the different stocks stays the same over time. But in reality, whenever the market crashes, which is what we want protection against, those relationships between the stocks change and they all tend to kind of behave the same. So we're actually paying a little more on the upside than the protection we're getting on the downside. So we're sacrificing a little more profit by spreading ourselves a little thin. Then we are getting protection on the downside. No, that's not a bad thing. That's just essentially a price that you pay for what amounts to insurance. So you're kind of insuring against downward market movements, but the nice mathematics of the you should diversify argument rely on an assumption of those relationships between the stocks not changing over time, and in reality they do. So that's what this is more in relation to. Again, more for my stats class, but I think the idea of being aware of our assumptions is very important across all of math. Okay, so last time we discussed what rational expressions are and how to simplify them. So we saw that rational expressions are a ratio of two polynomials. And now we're going to work on operations on rational expressions. We mentioned last time that rational expression is a ratio. It's one thing divided by another. It's basically a fraction. And the simplest polynomials, I suppose, we could have are constants. So we could really just think of rational expressions like, 3/2 or 1/3 or something like this. So if I want to multiply or divide rational expressions, first let's remember how to multiply or divide just regular fractions. So if I have something like 3/2 times 1/3, what is my rule? What is my kind of my assumption in a sense? What's my rule for how I multiply fractions? Well, when I have the product of two fractions, I just multiply across the top, multiply across the bottom. This is different than how I add fractions. When I add fractions, I don't add across the top and add across the bottom. We'll get to that in the next section. But for multiplication, I multiply across the top, multiply across the bottom. And now thinking back to last time, we have two factors on top, 3 times 1, two factors on the bottom, 2 times 3. Everything is multiplied. And I see I have a common factor of 3 that can divide out. Give me 1/2. What about dividing fractions? What about, say, 1/4 divided by 3/2? What if I have a fraction divided by a fraction? Well, if I have one fraction divided by a second fraction, you might remember the little phrase invert and multiply. That might ring a bell. I take my fraction that's after the divided by symbol, I invert it. Instead of c over d, I make it d over c. And then I change my division sign to a multiplication sign. And then, of course, I multiply as I did up above. So 1/4 divided by 3/2. And I know when you write these, especially by hand, sometimes this divided by symbol can look like a plus. So I'll try to, say it out loud a couple of times just to be clear about what symbol that is. But 1/4 divided by 3/2. We can invert the 3/2. It's a fraction that comes immediately after a divided by sign to 2/3. And then the divided by switches to a times. So 1/4 divided by 3/2 is equal to 1/4 times 2/3. And we know how to multiply fractions. We multiply across the top. And I know that my 4 is 2 times 2. So one of those factors of 2 will divide out from the 4, leaving me with one factor of 2 left. In the numerator, I have just a 1. And in the denominator, 2 times 3 is 6. So 1/4 divided by 3/2 ends up being 1/6. Okay, so how does this change? Let me zoom in here a little bit because these rational expressions can start to have a pretty small font when we have exponents like the x squared here, and when we're dividing, so we're trying to squeeze 2 of them on a line. Sometimes the font can get a little small, so if you have trouble seeing any of these, just let me know, but I'll try to remember to zoom in when needed. Okay, so what about when I have something like this? This looks a lot more complicated. It looks a lot more difficult than what I did up here. But the same fundamental rules, the same basic idea should apply. Maybe it's a little more complex. Maybe there's a few more moving parts, but the same basic idea should apply. If I have the product of 2 fractions, I multiply them like this. If I have the quotient of 2 fractions, I invert and multiply, and then see the previous step. So what about something like this? 5x squared over x squared minus 2x minus 24, that rational expression, that fraction, times x squared minus 16 over 15x. Well, I kind of do the same thing that I did above. I say this is equal to, while I'm multiplying 2 fractions, I just multiply the numerators. And I multiply the denominators. Now, again, my numerator and denominator look pretty messy, a little more complicated than what I had up here. But what is the basic idea? Well, the basic idea is now I want to search for common factors between the numerator and denominator. That might mean, if I had a number like 12 up here, that might mean I need to think of the factorization of 12. Like, okay, well, 12 has a factor of 2. It's 2 times 6, but then 6 is 2 times 3. So I might have to, think what are the factors of my number in order to find common factors. I might have to think, what is my polynomial factor 2? Does x squared minus 16 factor into the product of 2 linears? I might have to factor my polynomials to try to identify common factors that I can divide out. Same idea here as in the example with just numbers. There's a couple approaches here strategically. I like to, I think I've even said this in a past example. At this point, we've gotten a fraction here that's pretty complex. There's just a lot going on. I prefer to decrease complexity before increasing it again. So I would start looking for common factors here. Some folks say, well, I prefer to factor everything at first and then look for common factors, right? It's kind of the question of if we took an example like this and we said this is 3/2 times 12 over 3, 3 times 12 over 2 times 3. Some people might prefer to cancel the 3's first and say this is 12 over 2, and this is 2 times 6 over 2, divide out the 2's and make that a 6. Other people might prefer to go from this step and say that's 3 times 12 over 2 times 3, and then factor everything here. 3 times, what does 12 factor into? 2 times 6, or 2 times 2 times 3 over 2 times 3. And then once you have everything kind of broken down, divide out at that point. I think it's 6 of one, half dozen of the other. I think it's about the same either way. My preference is usually at each step, let's simplify as much as we can. So I kind of see this strategically. I'm going to have to end up factoring this x squared minus 16 and this x squared minus 2x minus 24. But I also might notice that I currently have some common factors that I can pretty easily see and pretty easily divide out. I see I have a factor of 5 on top, and my 15 is 5 times 3. So the 5 on top divides out the 5 from the 15, leaving me with 3. And I have a factor of x on the bottom that divides out one of the factors of x on the top. When I do that simplification, I get an x left over on the top times x squared minus 16 over, and on my denominator, I have a 3 times x squared minus 2x minus 24. This is the way that I would usually do it. At each step, divide out everything that I can so that I'm kind of simplifying before making things look more complicated again. But I don't think there's really anything wrong with somebody who would have started by factoring x squared minus 16 and x squared minus 2x minus 24, gotten everything broken down to the smallest factors, and then started dividing out. Give me 1 second here. Sorry, it's my crazy allergy season, and I don't want to sneeze in your ears in the microphone. Okay. So like I said, either way is, I think, equally valid. This is the way that I'll tend to do it, but if you prefer to factor first, no big deal. Okay, so now I notice that x squared minus 16, it's kind of a little bit like the 12 up here, that it can be factored into simpler components that might end up dividing out. I recognize x squared minus 16 as a difference of squares. And I know that that pattern factors into, so this is x squared minus 4 squared, factors into x minus 4 times x plus 4. Looking at my denominator, I have x squared minus 2x minus 24. And again, I could start from first principles and factor this. But remember that what I kind of mentioned last time, there's, especially if you're on an exam or something, there's an element of test taking strategy. You say, well, you know, these rational expression problems, if I just encountered one randomly in some kind of other context, maybe I wouldn't expect simplification here. But if it's a textbook problem, I suspect that, you know, there's probably going to be some simplification that happens. I wouldn't be at all surprised if either x minus 4 or x plus 4 was a factor of x squared minus 2x minus 24. So I can, as they sometimes say, use the test to take the test, right? If I expect that, you know, probably more than likely there's going to be a common factor that I can divide out, because that's kind of the thrust of this section. Well, that kind of leads my search, that guides my search a little bit. I'm looking for two numbers that multiply to negative 24 that add to negative 2, and I do see that positive 4 and negative 6 fit the bill. 4 times negative 6 is negative 24. 4 plus negative 6 is negative 2. That looks good. And I see that the factor of x plus 4 will additionally divide out. And this leaves me with this rational expression. I would probably leave it here. Unfortunately, in some contexts, what's the simplest form can be a little bit ambiguous. I think this is a perfectly fine way to leave it. probably something like x squared minus 4x over 3x minus 18. I would say that that's, in my opinion, equally simplified. But for instance, this is not simplified because there's a common factor we can divide out. So at the very least, we want to divide out all of our common factors. And I would probably tend to leave it in the factored form, although I would, argue that philosophically that I think this form, provided that we have divided out all the common factors, is just as simple as the one in the box here. But the nice thing about the one in the box is you can readily just look at it and see that there are no common factors. Okay, let's do a couple of practice problems. Or well, let's do one practice problem to start. Zoom in. There we go. I usually have this zoomed where I want it, but then when I when I shut down and restart OneNote, it zooms everything back out again. So I think that should be big enough for you to see. So let's take about maybe about 2.5 minutes to go through this one problem. Just work through this one, multiply the two rational expressions, factor, simplify, and get you the final answer. So 2.5 minutes or so, and then we'll come back and discuss. Okay, so let's take a look at this one. I think this was pretty straightforward. So again, we multiply two fractions by multiplying across the top, multiplying across the bottom. So we get y squared plus 3y times y minus 4 over y squared minus 3y minus 4 times y squared. I don't see any common factors yet. There's nothing I can simplify at this step. So I'm going to go to my next step. I'm going to factor everything. Y squared plus 3y has a greatest common factor of y they can factor out. Y times y plus 3. That's as simple as that can get. And then the y minus 4, nothing we can really factor out of there. That's just y minus 4. In the denominator, my y squared just stays as y squared. But my quadratic, my y squared minus 3y minus 4, that might be able to be factored, looking for two numbers that multiply to -4, that add to -3, I think that's -4 plus 1. So y minus 4 times y plus 1. That does work. And then I noticed that there's a factor of y minus 4 in both the numerator and denominator. I divide those out. The factor of y in the numerator cancels with or divides out one of the factors of y in the denominator, leaving a single factor of y left over in the denominator. And when I collect all of the stuff that's left over, I get y plus 3 on top over y times y plus 1 in the denominator. Now, something that we want to be really careful about, a mistake that's easy to make if we're not being careful, is to, at this step, to do something like this. We might like try to divide out a y squared. We might say, oh, I see a y squared on the top and bottom like this, or maybe even like this, and try to divide it out. Or maybe I would say, oh, maybe I can divide out this -4. I have to be really careful not to do that. I have to be very careful that anything that I divide out, I'm only looking for things that are entire factors that are connected to the rest of, say, the numerator with a times sign, or that are connected to, say, the rest of the denominator with a times sign. Only things that are connected to the rest of the numerator and denominator with a times are kind of eligible to be factored out as a complete unit. If we were to say, think of -4 that we see on the top and the bottom, yeah, I see a -4 on the top and the bottom, but it's connected to these other terms, not with a times sign, but with plus or minus. And same thing here. So I would not want to say, try to divide out -4, or try to divide out y squared like this or like this. Now, if, in a different problem, if I had, say, a factor of y squared out in front, if I had y squared times y squared plus 3y times y minus 4, this y squared is connected to the rest of the numerator by a times. So this would be eligible to divide out that one in the denominator, which is also connected to everything else by a times. So very important note. We just want to be super careful. We don't want to just say, because I see a similar looking thing in the numerator and denominator, I can divide it out. I have to make sure that the thing that I'm dividing out as a factor is something that's connected to the rest of the numerator and denominator by a times, not by a plus or minus. If it's a term, if it's connected by a plus or minus to everything else, then I can't divide it out. Okay. So what about dividing rational expressions? How does that work? Well, again, let's think back to our just numerical fractions. 1/4 divided by 3/2. What did we do? Remember, we said we needed to invert and multiply. We take the fraction that is immediately after the divided by sign, we flip it so the numerator becomes the denominator, denominator becomes the numerator, and then we change the divided by sign to a times sign. What do I have here? I have rational expression divided by rational expression. Again, looks a lot more complicated. There's a lot more going on. There are x's and x squareds and so on. It looks more difficult, and it is, in a sense, more difficult. But these same ideas apply. At the end of the day, I just have fraction divided by fraction. And this is a problem that requires more steps to solve, but I can chip away at it. I can sink my teeth in somewhere, right? That's another maybe test taking strategy as we're working towards exam 3 or the unit 3 exam unit 2 exam, and the final exam. My other class has 3 exams. As we're working towards these exams, sometimes test taking strategies are helpful to think through. And if you look at this problem and you say, not that this would be on the exam, but just as a general strategy, if you say, wow, that looks like a really complicated problem, there's a lot going on there. I can't see the path from the start to the end. Well, ask yourself, can you take one step forward? Is there one thing you can do? And one thing that I can do is I notice that I have a divided by a fraction. I know something I can do there. I can invert and multiply when I have that pattern. So my first fraction stays the same, but my second rational expression, my second fraction is after the divided by sign. So I'm going to invert. I'm going to swap the numerator and denominator. And my divided by sign is going to turn into a times sign. Well, now, as we like to say in math, we've reduced the problem to a previously solved problem. Now, instead of dividing two rational expressions, I'm multiplying two rational expressions, and I know how to do that. I can take one more step, even if I don't see the strategy to get all the way to the end, even if I'm not even thinking about dividing out common factors at this point, that's fine. I can take one more step. Sometimes that's, a good mental approach. If you get a little overwhelmed on a problem in an exam, is there one step I can take? Yeah, there's one step I can take here. I know that if I have the product of two fractions, I multiply the numerators, I multiply the denominators. That's just a rule. That's a property of how fractions work. And again, I look at this and I say, okay, what is my end goal? My end goal is to simplify. In order to simplify, I know that to simplify a fraction, I want to divide out common factors. Can I get common factors here? Right. You might, if you take a step forward, you might make a mistake, like, let's say distributing. You might say, oh, can I distribute this 24x squared into these three terms? Yeah, I mean, we could, but if you tried to do that, you would end up with something x to the fourth and x cubed and x squared. And you would pretty quickly realize, okay, that became a big mess. Maybe that wasn't the right path, right? So that's the other thing with test taking strategy is, on occasion, you'll go down the wrong path. If you can see the strategy from beginning to end, that helps keep you on the right path. If you can't see the strategy from beginning to end, taking one step forward at a time is often helpful. But each time we take a step forward, we want to re-look at the problem and reevaluate the problem and say, can I see the strategy to the end at this point to help direct my path? I wouldn't want to say distribute here. Although if I did, I would realize that maybe that was the wrong path. I just back up a step, say, is there something else that I could do at this step instead of, say, distributing or something? Well, sure, instead of that, I could factor. I don't see any common factors right now. This denominator is actually already factored pretty nicely for me. Let me focus on factoring the numerator and then see what happens. We might need to go a little bit further, but let's factor the numerator first. I'm looking for two numbers that multiply to 32, positive 32, that add to negative 12. I think this is going to be -8 and -4. I know that 32 is, I could have 1 times 32, 2 times 16, or 4 times 8. That's really my only choices. 32 is a power of 2. So my only prime factors of 32 are 2's. So there's not a whole lot of choices for its factors. And -4, -8, add to -12. So I think this is going to be x minus 4. Oops. Times x minus 8 on the top. Now I still don't see any common factors. But again, I can look a little more closely. X minus 4, x minus 8, there's nothing more I can do to that. 24x squared, that's just what it is, just a monomial. But if I look a little more closely at my denominator, I realize, oh, okay, well, these are linear factors, but there is something else that I could do here. I actually could factor out a greatest common factor, at least from the first one. Four x minus 16, both terms, the 4x and the 16, have a factor of 4. So I could factor this into 4 times x minus 4. Wait, can I do that with the second factor in the denominator? Is there a common factor between 3x and 24? Yeah, I think I could actually factor a 3 out of there. I'll just write it like this. I'll put parentheses around the 3 just to be clear. Sometimes when we have like parentheses, number, parenthesis, it just looks a little funny. But if I factor the 3 out, I'm left with x minus 8. Right, so maybe I didn't see right away that I needed to do more factoring in the denominator, but if I chip away at it step by step, even for a big problem like this, that can sometimes make the problem more manageable. And now I do see common factors. I see an x minus 4 and the top and bottom, again, being very careful that this is multiplied against everything. So that makes it a factor. It can be divided out. I also see an x minus 8 that I can divide out. Let me just take a minute here and write this again. There's just a lot going on here, so I've divided out a couple of things. I'll just copy it over. Sometimes when you divide out too many things all at once, it can be a little hard to just visually keep track of what was divided out and what wasn't. So we divided out a couple of things. We'll rewrite. Now I see a 4 in the denominator. Is there a factor of 4 in 24? Well, sure there is. 24 is 6 times 4. I also see a factor of 3 in the denominator. Is there a factor of 3 in that 6? Yep, 6 is 3 times 2. So all of this boils down to 2x squared. We had a ton of stuff cancel out, a ton of stuff divide out, and this whole big complicated quotient of 2 rational expressions just boil down to this relatively simple polynomial, 2x squared. Now, one thing that I do want to be a little bit careful of is when I say equals here, I'm saying the left-hand side and the right-hand side are the same thing. They represent the same thing. Well, I do realize that 2x squared, I can plug in any real number into here and get an output, and that's not going to cause a problem, right? I can plug in -5 or +10 or 0 or anything like that into 2x squared. I could get an output, no issues. But if I look at my original expression, can I plug in, say, x equals 4? Well, no, because that would give me some fraction with a 0 in the denominator divided by something else, but I can't divide by 0. So up here, I can't plug in, for instance, x equals 4, but down here it looks at a glance like I could. I better, if I'm going to say these are equal to one another, that this initial expression is equal to 2x squared, I better make the note that that's only when x is not equal to 4, for instance, right? I better explicitly state my restricted values if I'm going to say these are equal. Well, are there any other restricted values? So I have restricted values when, say, 4x minus 16 equals 0, when the denominator of the first fraction is 0. That's one place that I have restricted values. That's when x equals 4. That was just what I showed a minute ago because it was simple to figure out that plugging in 4 gives me a 0. I have a second fraction, this one here, 3x minus 24 over x squared minus 12x plus 32. this has a 0 in the denominator anytime that x squared minus 12x plus 32 equals 0. So I have a first fraction. We have restricted values anytime the first fraction's denominator is 0, which is when x equals 4. We have a second fraction that we're looking at here. Anytime its denominator is 0, we also have a restricted value. Now, if I look through my problem, through the work that I've done before, I see that x squared minus 12x plus 32 factors as x minus 4, x minus 8. Again, using our zero product property, x minus 4 times x minus 8 equals 0 means either x minus 4 is 0 or x minus 8 is 0, which means either x equals 4 or x equals 8. So I've picked up another restricted value in addition to the x equals 4, which is just repeated here. So x cannot be 4 or 8. And then it's a little tricky because I actually have a third fraction here, don't I? I have one thing divided by another thing. Or in other words, when I kind of do my invert and multiply, kind of the numerator of this second rational expression kind of becomes a denominator. So anytime 3x minus 24 equals 0, this whole second fraction will be a 0. And then I have number divided by 0 anytime that the numerator here is 0. So I actually pick up even another criterion for restricted values, that when 3x minus 24 equals 0, that's a problem also, because I have fraction divided by fraction, but when 3x minus 24 is 0, my second fraction is 0, so I have something divided by 0 there as well. I really have kind of like three denominators, two that I see explicitly, and one that's from the fact that I have fraction divided by fraction. So the second fraction as a whole is kind of in the denominator. 3x minus 24 is 0. Isolate the variable term, 3x equals 24. Isolate the variable, divide by 3. X equals 8. Okay, we just got a repeat of x equals 8 in this case. But we could have, in a different problem, gotten a new restricted value. So we have to be careful that in something like this, we're just very careful about where could a 0 occur in the denominator. There's actually three different places. When 4x minus 16 is 0, when x squared minus 12x plus 32 is 0, and even when 3x minus 24 is 0. Note that 24x squared being 0 is not a problem. It's in the numerator of the first fraction. So if it's 0, it's just 0 over some number, which is just 0. And it's not after a divided by sign. So the 24x squared, I don't care if it's 0 or not. I can plug in x equals 0 with no problem. But again, it's crucial that if I'm going to say that this expression is equal to this one, that I make sure to note that that's not true for x equals 4 and x equals 8. Because naturally, I usually would be able to plug 4 and 8 into 2x squared without a problem, but I would not be able to plug those values into this original expression. Okay, so let's look at these two. We'll take probably about 5 minutes. Let's go with about 4 minutes to go through this one. I think we're getting pretty decent at factoring. So let's go with 4 minutes for this one. And then if you finish a couple minutes early, you can start working on the next one. How would it look if we have fraction times fraction divided by a third fraction? So think about that one. And if you're not sure what to do there, again, just kind of take it step by step. Is there something that you can do that you know how to do? So, well, let's take about 5 minutes. That'll give you plenty of time to do this one. And then if you get done early, you can start thinking about this one as well. So in about 5 minutes, we'll come back. We'll discuss this one. I definitely don't expect you to get through both of them in 5 minutes. But if you get through the first, start looking at the second and think, how would you handle kind of an order of operations problem like this, where we have a couple of different rational expressions multiplied or divided? So 5 minutes in, we will discuss the first one. Okay, it's been about 5 minutes. Um, so for this problem, the first thing that we do is we invert and multiply in our second fraction. And then we know that multiplying two rational expressions together, we multiply the numerators, multiply the denominators. So we get 8x squared plus 15x minus 2 times, after we invert, the numerator is going to be x, it's going to be x squared plus 16x plus 64. And then our overall denominator is going to be x squared minus 64. And then again, after we invert and multiply, the denominator is going to be our 8x squared plus 63x minus 8. I don't see any common factors right away. It would be super nice if, this 8x squared plus 63x minus 8 was, say, like an 8x squared plus 15x minus 2, and I could just divide out those whole big factors, but not so. So I look at each of these, I say, okay, I actually have 4 quadratic expressions here. So all of them are candidates for being factored. X squared minus 64, difference of 2 squares, factors into x minus 8 times x plus 8, x squared plus 16x plus 64. Maybe I recognize this as the perfect square pattern. I note that x squared is just x squared, and 64 is 8 squared. So then as my cross term, my middle term, is it 2 times x times 8, plus or minus? Yes, it is. It's a perfect square. So this is x plus 8 squared, or x plus 8 times x plus 8. I could also have just noticed that I'm looking for 2 numbers that multiply to 64 and add to 16, and 8 and 8 fit the bill. My other 2 quadratic expressions are a little harder to factor. I don't really notice anything like a perfect square pattern or anything like that to help me out. So I'm just going to factor these with AC grouping. They're a little too complicated, I think, to do guess and check. If you wanted to try guess and check, you could, but the problem is that this factor of 8 in front of the x squared could factor as 1 times 8 or 2 times 4. And so you're going to have several different possibilities for, and also our last term is a negative. So it could be, a -2 and a +1, or a +2 and a -1, and so on. So just lots of different possibilities. It's going to be really hard to guess and check for either of these. So just use the AC grouping method. For the one I've kind of labeled green here, the top left, 8x squared plus 15x minus 2, a times c is -16. I'm looking for 2 numbers, m and n, that multiply to -16 and then add to +15. I think that's plus 16 and -1. And I've shown the details over here for how this factors into x plus 2 times 8x minus 1. And then the one that I've labeled red, this bottom right, 8x squared plus 63x minus 8, similar process. A times c equals 8 times -8, or -64. Looking for 2 numbers that multiply to -64 that add to +63. And I think that's plus 64 and -1. And again, I've shown some detail here for how this factors to x plus 8 times 8x minus 1. And now I'm going to search for common factors and start dividing them out. Well, I have 2 factors of x plus 8 on the top coming from that perfect square on the right here. And nicely enough, I actually get 2 factors of x plus 8 on the bottom. Those all factor out. Or sorry, those all divide out. And I also have an 8x minus 1 on the top and the bottom. Those divide out. This all leaves me with just x plus 2 over x minus 8. Sorry, when I zoom in, my line thickness gets bigger, and then I have to write a little bit bigger. And again, I want to be aware of the fact that I'm claiming that this expression I've written down at the bottom is equal to this big expression up here. Well, I need to state my restricted values. So these are only equal to one another under the restriction that x is not equal to what? Well, when x squared minus 64 equals 0, I have a problem. Or that's whenever x minus 8 times x plus 8 equals 0. Or when x is 8 or negative 8. I pick up those restricted values here. When is x squared plus 16x plus 64 equals 0? I've already done the work to factor that. That factored into x plus 8 times x plus 8. When is that product equal to 0? Only when x equals negative 8. I've already got that listed, so I don't have to add anything on. And again, the one that's tricky that I can easily miss is when is this whole second fraction 0 because we're dividing by it. In other words, when is the numerator of the second rational expression equal to 0? 8x squared plus 63x minus 8. When is that 0? Well, that's when x plus 8 times 8x minus 1 equals 0. What x plus 8 equals 0 is just when x equals negative 8. I've already got that listed. I don't have to append anything to the list. But 8x minus 1, when is that 0? That's when x equals 1/8. I better put a 1/8 down there as well. So these are my 3 restricted values for this problem. It's only proper to say that the original expression equals the simplified x plus 2 over x minus 8 when x is not plus or minus 8 or positive 1/8. Okay, any questions on this problem? So we can see these are definitely not easy problems. This is, certainly the kind of the capstone chapter of the course, because we see that it's really incorporating everything that we've done so far. If you struggle with factoring, if factoring didn't really make too much sense in chapter 7, chapter 8 is going to be very difficult because you can see we're working with polynomials, with quadratic expressions, and we need to be able to factor them to really do a lot of this, to either divide out common factors or to find restricted values, or a lot of what we do starts with factoring. So if you're, feeling a little bit uneasy about chapter 8, that's one thing that you might want to ask yourself is, how do you feel about factoring? Do you feel like you don't understand factoring very much at all? Or do you feel like, oh yeah, I got through chapter 7, but it was a real struggle, like I kind of, barely understand factoring? In either of those cases, maybe go back to chapter 7, pick, 5 or 10 problems from the book or from WebAssign and just go through, 5 or 10 randomly chosen factoring problems each day until you drill it in and you get that practice and you get used to doing it. If you feel good about factoring, if you're like, yeah, chapter 7 went great, but you're a little confused, then maybe look at some of the other things, like how are you with your fraction properties? Are these properties kind of like second nature to you? Can you do these without even thinking about it, or do you have to be really careful and think a lot about properties like these ones, or like how to simplify numerical fractions? If that's the hang up for you, then maybe going back to the beginning of the book or something like Khan Academy or something like that, and just practicing some of the basic fraction properties, that might be helpful, right? We're combining a bunch of different ideas here. All right, if I can get there we go, my cursor to go where I want it to go. So we're going to do one more problem on the worksheet before we switch back and move on to the next section. You can also tell that these problems just take a while to do, right? They just take a little bit longer. So you need to be have a little more perseverance. That's another, thing to just note about these problems, that if it's taking you 4 or 5 minutes to do one of these problems and you were saying, wait, in chapter 7, it was taking me like 30 seconds or a minute to do a bunch of the problems. that's just kind of the nature of rational expressions. It just takes a little bit longer to do these problems. So, it does require a little bit more perseverance. There are more steps until we get to the answer at the end. So take a look at this problem. We'll take again about 5 minutes or so to work through this problem. And just kind of as a hint, if you take it step by step, if you want to kind of approach the problem as one whole problem, you can do that. But if you don't want to, you can start with these two rational expressions, these two fractions. You can forget about this piece here for the time being. Just look at these two, simplify these down to a single rational expression, and then tag on this second rational expression and go from there. Right? Similar to how if I had like 1/2 times 3/4 divided by, 1/7 or something, I could just do 1/2 times 3/4 first, get an answer. What would that be? 3/8, and then divided by 1/7. And then I recognize this pattern. So you can either try to approach the problem as one big problem or as two smaller problems. If you're feeling pretty confident, maybe going with one bigger problem will be a good challenge. If you're feeling a little uneasy, focus on these first two, multiply them, simplify as much as you can, get them under a single rational expression, and then take that rational expression divided by this one, and then go through the same process a second time. All right, so about 5 minutes, we will come back and discuss. Okay, it's about 5 minutes. So again, this was a pretty involved problem. So we can start by just taking these first two rational expressions multiplied together, figure out what they are. So 3x squared plus 24x over 3x plus 2 times 3x squared minus x minus 2 over x squared plus x minus 30. I know multiplying these together, I'm just going to multiply the numerators, multiply the denominators. So I'll do that in one step while I factor. 3x squared plus 24x has a common factor of 3x. And then what's left over is an x plus 8. And then my other numerator, I can use guess and check or AC grouping to see that my other numerator factors to 3x plus 2 times x minus 1. So I have all of these factors in the numerator. And then for my denominator, I have 3x plus 2. Nothing I can really do with that. And then times x squared plus x minus 30, but that's x plus 6 times x minus 5. I note that at this step, the 3x plus 2 divides out, so I can get rid of that. And this first product simplifies down to what I have down here. 3x times x plus 8 times x minus 1 in the numerator over x plus 6 times x minus 5 in the denominator. Now I want to take this fraction and divide by this other one. So I have my black rational expression over here, 3x times x plus 8 times x minus 1 over x plus 6 times x minus 5. Then I'm dividing by my green rational expression. Remember, that means I invert and multiply. That means the x plus 6 gets tacked on in the numerator, and the 72x squared minus 84x gets tacked on in the denominator. Right away, I see I have a common factor of x plus 6. I can divide that out. I'm left with 3x times x plus 8 times x minus 1 in the numerator divided by x minus 5. And I might notice that, okay, 72x squared minus 84x has a common factor of x I could factor out. Looks like maybe I have a common factor of 4 that can come out, or I can at least see that there's definitely a common factor of 2. So I can factor this to something like 4x times 18x minus 21. I see that my x's divide out. But after I factor out a 4, I realize that, oh, 18x minus 21, there's additionally a factor of 3, common factor of 3 there, that can also factor out. So 18x minus 21, I could think it was 3 times 6x minus 7. And that 3 in the numerator divides out with that one. If this was too much for one step, no problem. You can always just split it into a couple of steps. It's a little more writing, but if it keeps you from making an error, it's worth it. But I see the 3x in the numerator divided out, and I'm left with x plus 8 times x minus 1. In the denominator, I'm left with x minus 5. I'm left with this factor of 4. Maybe I'll put that out in front. So I got the x minus 5, I got the 4. And remember, my 18x minus 21 factored into 3 times 6x minus 7. I got rid of the 3. I have a 6x minus 7 left over. Is there anything else that can be factored or divided out? I don't think so. So this should be the simplest form. Again, I want to mention my restricted values. So these two expressions, this original big expression and this more simplified, although still not super simple expression, they're only equal when under the restriction on my domain, under the restriction on my inputs, I can't plug in any x that makes this 0, or that makes this 0, or that makes this 0, because obviously those inputs would make a 0 in the denominator of a fraction. We're not allowed to do that. But also I noticed that I'm dividing by this last fraction here, so I can't have any x inputs that would even make this one 0. So I have 4 equations to solve for my rational expressions, or sorry, for my restricted values. So let's just come over here off to the side. When is 3x plus 2 equals 0? That's when x equals negative 2/3. So I can't have negative 2/3. When is x squared plus x minus 30 equals 0? Again, let me look back at my work that I did before. I know that this factors into x plus 6, x minus 5. That's 0 when x is negative 6 or positive 5. When is x plus 6 equals 0? Well, of course, that's just when x equals negative 6. We've already got that one taken care of. We don't have to append anything. And then when is 72x squared minus 84x equals 0? Well, we know that factors into what? Well, 4x times 3, that was 12x times 6x minus 7. Or that's when x equals 0 or x equals what? 7/6. So all kinds of restricted values here. These two expressions are only equal when x is not equal to any of these 5 numbers. We kind of see an implied restriction of x equals 5 and x equals 7/6 still existing in this simpler rational expression. So I suppose if we had left out the 5 and the 7/6, we wouldn't have done anything, too egregious, because the domain restriction is still implied in the simpler version as it is in the original version of the expression. But we lost along the way with dividing things out, we lost the information that x cannot be negative 2/3, negative 6, or 0. When we divide it out, when we divided out x plus 6, we lost the it cannot be negative 6 piece of information. When we divided out the 3x plus 2, we lost the negative 2/3 restricted value. And when we divided out the x, we lost the x equals 0 restricted value. So dividing things out lost some of that information for us. So we had to be careful to, in a sense, add it back in. Any questions so far?
I have one. I don't know if it's a silly.
So again, these problems can look overwhelming at first. That's definitely true. There's just a lot going on. But I think if you do feel overwhelmed at any point, just saying, okay, is there something I can do? Even if it's not the right thing, maybe you do something and get on the wrong path and have to back up and try something else. Is there something you can do? Okay, so 8.3.
Excuse me?
Moving into adding and subtracting rational expressions with like denominators. So we're looking
Professor?
at examples like this one, where both rational expressions have the same denominator. Yeah, question.
Can you hear me? Professor? I don't think he can hear us.
If you're talking, I think you might be muted. Oh. Okay, I actually had myself muted. Sorry about that.
Yeah, you're good. It's just Imani had a question and you couldn't hear us, so she
okay.
wasn't able to ask her question. I didn't want you to move on too quick before she was able to ask it.
No, thank you. I actually had my my sound muted, so I appreciate you pointing that out and raising your hand. I do have chat open, but so thanks for letting me know. Yeah.
No.
So question.
Yeah, just one question. So for the problem that we just did,
Mhm.
Whenever we were factoring the 72
Mhm.
x squared, I just originally pulled out the 12x before I got started with everything.
Yeah.
So I guess my question is, like, in case I were to not realize that like the 3x and the 12x go into each other because I pulled it out that way, like, is that something that I might get like partial credit for, or does that make sense?
Yeah, definitely. Um, so absolutely, like here, so that was great to recognize that, recognizing immediately that 12 is a factor of both 72 and 84 can be pretty challenging. But oops, that was a little more than I wanted to erase.
Yeah,
Sometimes
but
this
I
big
feel like
erase.
since I pulled that out first, it might be like I might actually make that mistake, if that makes sense.
Yeah, absolutely. Um, so that was why I kind of started with a smaller factor coming out, because I think, that would be really hard to see. But if you saw that, that's great. So we'd end up with 12x times what? 6x minus 7. So if you did something like this and you saw that, okay, the x's divide out, but maybe didn't realize that that this 3 up here divides out into the 12. Yeah, so first off, if you wrote, if this was 3 and 12, if that was your answer in WebAssign, WebAssign would probably mark it wrong. But in an exam or something like that, when I go through it, I look at all of the things that WebAssign marked wrong, then I would give you, the vast majority of the credit for this. So to answer that one question, yeah, that definitely would earn you most of the credit. But it's also, something that I suppose I've kind of glossed over is factoring the quadratic expressions is kind of the meat of the problem. But we also still want to factor our numbers. So we think of 12 as being like 2 times 3, and 3 as being prime. So we now kind of see that the threes divide out. So that's a really good point, is we're focusing so much on the quadratics that we might forget about something like this or something like this, right? So we have a numerical part as well that we want to make sure that we kind of factor and attempt to divide out any common factors there too. So we would get a prime factorization. Oops, bounce me to the top. There we go. We would get a prime factorization for the numerical factor in the numerator denominator, and then see if anything divides out. But again, if you didn't see that right away, or if you missed that and you got to something like this where you had a 3 over 12, yeah, you would get the vast majority of the points for that. But kudos on seeing that 12 was a factor of 72 and 84.
Thank you. I really appreciate that. But then this is like where I make all my silly mistakes because I might not see the 3 and the 12 after I did all the steps.
Yeah, and it's kind of unfortunate. It's like you're so focused on the more difficult stuff that sometimes those, for lack of a better word, the simpler stuff gets lost in the shuffle. And I think also some of that comes with just experience with the problem type, right? When you're first looking at problems like this, um it's so new and maybe a little bit overwhelming that you're so focused on the quadratic stuff, because that's where kind of the novelty is, that it's easy for some of the simpler stuff to kind of fall by the wayside. But if you go through 10 of these problems or something on the homework, then it becomes a little bit more a little more recognizable, a little bit less of a kind of a steep climb. So then you can kind of incorporate those simpler bits back in a little more easily. So I remember like it's gonna seem like a completely off topic thing, but back when I was in college, I did ballroom and swing dancing. So it was super fun, met a lot of great people, but um, there were like some very basic steps or very basic ideas, like, what count you're on or whatever, or like making sure uh that you're matched up to the music, that kind of thing. So these are basic ideas, right? And you know, if you've been doing it for a couple of years, that's like pretty like autopilot. But then if you're learning some new complicated move or some complicated step, then you tend to like, even if you've been doing it for a few years and you're like, oh yeah, I can, you know, keep my steps to the music, that's not a problem at all. When you're doing the complicated step, it's like you end up getting off of the music or getting off of the timing, or so the simple stuff just falls apart because you're focusing so much on the new idea that's not really ingrained in the muscle memory yet. And then it just takes some time to get that ingrained to the point where you can then kind of marry those two things back together. So I think it's kind of the same thing here. It's there's so much focus on the new stuff with all of the quadratics and the factoring and the canceling, that sometimes that prior knowledge kind of falls by the wayside for a little bit until you get kind of comfortable with the more advanced stuff, and then everything kind of comes together again.
Yeah, I feel like my brain's like making room for all this, and it's like almost forgetting everything else.
Yeah, exactly. And that's also something that you can, like, if you want to make a note to yourself, if you do these steps, or if you write out the steps, do these 5 or 6 steps or whatever to, simplify a rational expression. If you know that that's something that you tend to forget about or skip over, you can add like a step, whatever, like 5B or something like that. Check and make sure any of the numbers, whether any of the numbers factor. So if you recognize that as something that you tend to miss, then that's also something that you can take extra caution to double check. Yeah. All right. So I do have my sound unmuted now. So if anybody has a question now, now I will hear you, or you can always pop it in chat too. Okay, so adding and subtracting rational expressions with like denominators. So again, we have 2 rational expressions here, same denominator. We want to add or subtract them. How does this work? Well, let's again think back to something like 1/4 plus 5/4, let's say. Again, in a sense, just numerical fractions are kind of like the simplest rational expressions. So how does this work? If I have A over B plus C over B, what is the fraction property? Well, when I'm adding or subtracting 2 fractions with the same denominator, their sum or difference has the same denominator. It's not B plus B, it's just the same denominator of B. And the numerator is A plus C. Right? In other words, well, let me come over here. In other words, if I had like 2 pizzas, or I guess a little more than 2 pizzas, but like this, and the pizzas were originally sliced into quarters. If I have 1/4 left in this pizza, I have this area. If I have 5 quarters left of these pizzas, I have 1, 2, 3, 4, 5. When I add them together, when I kind of reallocate the slices so that I can get rid of some pizza boxes, my pizzas are still divided into quarters, right? The slices that I have are still quarter pizza slices, but I have 4 of them from here. I have 1 of them coming over from here, and then I have another one coming over from here. My denominator stays the same. My slices are quarter pizza size slices. So that doesn't change from the left side to the right side. What changes is I'm taking one slice of pizza from the first bit and then 5 slices of pizza from the second bit and kind of combining them together, and that makes a total of 6 slices of pizza. So super easy thing to do is to kind of get the multiplication rules or division rules and the addition or subtraction rules kind of mixed up somehow. It's super easy to think, oh, because when we multiply fractions, we multiply across the top, then we multiply across the bottom to get our new numerator and denominator. We might be tempted to think that when we're adding, we add across the top and we add across the bottom, and that's not correct. If we have the same denominator, we just add across the top and keep the same denominator. When we combine our slices together, the slices don't change size. They don't go from being a quarter of a pizza slice to an eighth of a pizza slice. It stays as quarter pizza slices. We just have more of them when we combine them all together. And then at this point, 6/4, again, we want to think of this as 2 times 3 over 2 times 2, simplify, and we see that that can simplify to 3/2. I could kind of glue my pieces together and get 3 half pizzas out of this. Okay, so what does this look like in the context of a rational expression then? Well, the idea is the same. I have a denominator of x squared minus 64. That kind of sets the size of the pizza slice, so to speak. And then I have 2 numerators. I'm subtracting these fractions. Well, this difference is just going to be a fraction with the same denominator as the original one. And the new numerator is going to be the difference of the previous numerators. Just like I added together my numerators here, I could also subtract the numerators. Whether I'm adding or subtracting, this works very similarly. I do need to remember to distribute my negative here. So if you wanted to take an extra step and make this minus 6x squared minus 14x plus 10, you could. Because we're running a little short on time, I will just jump over that and we get 7x squared minus 6x squared is 1x squared. Minus x minus 14x is minus 15x. Plus 46 minus a minus 10, that's plus 46 plus 10, or that's plus 56. And now I have a rational expression, quadratic on top, quadratic on the bottom. I don't immediately see anything that divides out nicely. So I'll go on and I'll factor. X squared minus 64, difference of 2 squares. 64 is 8 squared. This gives me x minus 8 times x plus 8. And my numerator, I'm looking for 2 numbers that multiply to 56 and add to minus 15. I think that's minus 7 and minus 8. Again, if we didn't see that right away, we can get a little bit of a hint by looking at the denominator and thinking, well, this is a textbook problem. Something's probably going to divide out. So this gives us a little hint. But we see it's x minus 8 times x minus 7 in the numerator. We get a factor of x minus 8 that divides out. So at the end of the day, this all equals x minus 7 over x plus 8. With the restricted values, x is not equal to negative 8, which we can see there, or positive 8. We divided out the factor of x minus 8, so we really need to make sure that we say that x cannot be positive 8. X not equal to negative 8 is still kind of implied, but x not equal to positive 8, very important we include that. Okay, let's do one problem here. We'll take about 2.5 minutes. I know that's not a lot of time, but take about 2.5 minutes, go through this one, and then we'll talk about the solution, and that'll take us to the end of class today.
Maybe I can sit back to this off and then we can go from there. Let's get up the window here. If they don't come through because you feel like you don't need to do all that for me, then
All right, so the key idea the key idea in this one is that we can make the denominators look the same by recognizing that 4 minus 7x is negative of 7x minus 4. So if I just multiply top and bottom by -1, then I can get a common denominator or a like denominator. Oh, I think somebody is unmuted here. Let's see. Okay. All right, so if we switch this plus sign to a minus, then we have a like denominator. We have 10x squared plus 21x minus 13 minus 3x squared plus 4x minus 1 over 7x minus 4. Right, 4 minus 7x is -1 times 7x minus 4. And that's where that minus is coming from. We simplify the numerator, we get 7x squared plus 17x minus 12 over 7x minus 4. And again, using a little bit of test taking strategy here, I'm saying, okay, if this is a textbook problem, I'm guessing that a 7x minus 4 might factor out. If I have a factor of 7x minus 4 in the top, what would the other factor have to be? Well, 7x times x give me 7x squared, minus 4 times plus 3 gives me minus 12. Does this work out? My outsides give me plus 21x, my insides minus 4x. That does give me plus 17x. So I used my surrounding knowledge to help me factor this. And I see a 7x minus 4 divides out, leaving me with x plus 3. You could, of course, have used AC grouping and done it from first principles, but we use the 7x minus 4 in the denominator to help us find the factorization. All right, I will stop the recording.